Good morning, everyone, and welcome to this Agro State of the Art talk. Today, we are going to have a presentation called Risk Qualify Mineral Resources and Reserves with Modern Statistics, which is presented by Dr. Clayton Deutsch, which is a professor of geostatistics at the University of Alberta in Canada. I think this is fantastic because it's clear that it attracts a lot of interest, registrants from over 27 countries, and definitely welcome everyone who has come along from all over the world by the look of it. So just a few words before we start the presentation, just a few words about Dr. Deutsch. He's a professor in the School of Mining and Petroleum Engineering in the Department of Civil and Environmental Engineering at the University of Alberta. He teaches and conducts research into better ways to model heterogeneity and uncertainty in mineral deposits and petroleum reservoirs. And prior to joining the University of Alberta, Dr. Deutsch was an associate professor in the Department of Petroleum Engineering at Stanford University. He also spent 3 years with Exxon Production Research Company and 3 years with Placer Dome. Dr. Deutsch has published 8 books and over 300 research papers. He holds the Alberta Chamber of Resource Industry Chair in Mining Engineering, and the Canada Research Chair in Natural Resources Uncertainty Characterization. In 2020, Dr. Deutsch was presented with the Engineers Canada Medal for Distinction in Engineering Education. So AGRU would like to thank Roger Cooper for his help in organizing this talk by Dr. Deutsch. Roger is a JSU geology graduate and the principal consultant geostatistician at Newmont Mining Corporation in Denver. So before we start and we give the microphone to Dr. Deutsch, I just please want to ask everyone to turn their video and microphones off. I want to let everyone know that this presentation will be recorded. And if you have any questions, all questions, please write them down in the chat. We will collect the questions and we will read them to Dr. Deutsch, or he may be able probably to read some of the questions and see themselves. And before we start, I'd just also like to thank our Agri Manager, Kyring for organizing these fantastic state-of-the-art talks. And I think now I should be able to give the microphone to Dr. Deutsch.
Okay, well, thank you very much. Thank you for the nice introduction. I should put less information on my website. No, I'm just kidding. Anyway, thank you very much for the introduction, and thank you all for being here this morning, this evening, wherever you are. So yeah, let me go. My plan, by the way, is to talk for about 45 minutes. It could go over a little bit, but that's the aim, and then we'll have time for questions for 15 minutes or as long as it takes. So let me get going here. Okay, so like I said, over in red, 45 to 60-minute talk, chat questions. I did post a website there. I'll give some more information at the end, but of course I do teach a lot of classes and whatnot. I'm just going to bring that to your attention. The context of my talk is that geostatistics has evolved. It's evolved a lot over the years. It still is quite specialized. It's not taught extensively at the undergraduate level, unfortunately, although that keeps me extraordinarily busy teaching industry professionals and teaching people at the graduate level. I'm going to give a bit of history. I know it's a state-of-the-art talk, so why do we need to know history? But I think knowing a bit of the context and the historical context is useful and important. So I'm going to talk about that. I'm going to go through some of the tools of geostatistics and try to convey to you why it is important and why we do this. So numerical geological modeling. Okay, here we go. Paradigms. I know this is a little weird, but this is the way I look at the world. It's mostly by cartoons, okay? So I think there's been, in my view at least, 4 major paradigms of numerical geological modeling. And I'm just leaving it general at geological modeling, but really what I'm talking about is having some form of quantitative assessment of rock properties in the subsurface, typically in the form of a block model that we can add up resources, reserves. We can base decisions on that. We can base mine planning on that. We can decide, should we drill more? We can assess value of information and so forth. So I'm not exactly talking about a conceptual model, not talking about how the geology was created and those kind of models. The word model is much abused. We all know that, but I'm going to use it anyway and abuse it. But these paradigms, I show the picture in the upper right there. That's a kind of a picture of the Turin papyrus. Of course, it will end up back in Egypt at some point, but that's the oldest known geological map. Almost everybody here would have seen that and maybe even studied it because it's actually quite fascinating. It was drawn to scale. It's appropriate legends and colors and everything else. And really, for years, creating maps and sections by hand was basically, that was geological modeling. And that was a paradigm for, thousands of years, frankly. This isn't the oldest map, it's the oldest known one. So I always think about that. And even now, creating good hand interpretations and doing geological mapping is a very important paradigm of geological modeling. The second one, and I show a picture that I took of Donnie Krieg, that's by the number 2 there. And what I think is Donnie Krieg epitomizes to me the second paradigm where basically, and this happened in almost all disciplines, there comes a time where people try to do with the computer, the machine, what they did by hand. Maybe not as good, you can't get as much interpretation into it, but it is repeatable, it is fast, and maybe sometimes it is good. So basically the concept of Krieging, and the equations are there because I know you'd want to see them. That Krieging is basically trying to create a hand map, a single deterministic estimate, but do it with the machine. So get the machine to do what we would normally do. The third paradigm, and I show a picture of Andre Journal there, and I show him because I think he, more than anyone else, championed the concept in geostatistics and geological modeling that we should quantify what we don't know. So you understand the uncertainty, you understand the geological variability. Whenever you look at a Krieged map or a Krieged model, it's going to be smooth with widely spaced data. It's going to be more smooth. And then you come to the point where, I don't know how many times I've heard in my career, the more you drill, the more complex the deposit gets. And I always smile at that because of course it doesn't get more complex. We all know that. It's just our simplistic understanding does, particularly when we use techniques like Krieging. So the concept is, in that third paradigm, is quantify your uncertainty, quantify what you know. You can extract a single estimate at any time you want, but you quantify your uncertainty and then use that for risk qualified decision making. This fourth paradigm, which is the one that I think we're in now, and I show a picture of Harry Markowitz. He got the Nobel Prize a number of years ago, and his Nobel Prize, one of the number one reasons for that was championing this idea of making decisions on the efficient frontier. And that's what's shown down on the lower left, or lower right there, sorry. And the idea is, if you map decisions into a space of risk and value, a rational decision maker would only accept a decision. Let me just get a pointer here to maybe help out a bit. So a rational decision maker would only make a decision that was on that, what's called the efficient frontier. If you're willing to accept a certain amount of risk, you're going to take the maximum value for that. If you're targeting a certain value, you would take a decision with the minimum risk to get that value. So the idea there is to actively manage the uncertainty. So it's not that, you see, the paradigm of Andre Journal was quantify the uncertainty, and then that was kind of the end. But that's not the end. The end is to understand the state of uncertainty, which is a state of nature. There's no way around it. When we sample 1/1,000,000th of the subsurface and there's geologic variability at all scales, there's no way we could know for sure what's happening. So that's the kind of the paradigms. Just to wrap up some of that, I just want to really reinforce that there's many locations in a deposit that we're characterizing. Typically, we would grid it. I know geology is not gridded, our models are. So we create some sort of grid blocks. They could be as small as 1 meter by 1 meter by 1 meter, even smaller sometimes. They could be as large as 20 meters by 20 meters by 20 meters. I mean, that's kind of the range. We have these blocks, and there's tens of millions of these locations, and there's many different variables. Increasingly, we model variables that add value. We model contaminants. We model geometallurgical variables. We model particle size distributions. We model different geochemical measurements and so forth, there can be literally hundreds of variables that are modeled at tens of millions of locations. And the space of uncertainty is virtually infinite. It is kind of fascinating. We can actually narrow that down a little bit and quantify what it is, but that's not for today's talk. We can calculate local uncertainty. We have the techniques to do that. But when we want to get the uncertainty at a larger scale, so we want to get the uncertainty within monthly, quarterly, yearly production volumes, we want to get the uncertainty within different parts of the mine plan, there's only one way to do it, which I know you're not going to be happy about. Nobody's happy to have one approach. This is it. But it's one methodology, which is simulation. But there's many ways to implement it. So don't worry, you have your choices. But creating multiple alternative realizations, not to sample the full space of uncertainty, that's silly. We'll never be able to do that. But we will sample hundreds, sometimes thousands of possibilities of what the deposit could be. That's these realizations. We're going to do it fair. And that's why simulation is the only approach. If you don't use simulation, you're going to inject some sort of bias or some sort of smoothing or some sort of misrepresentation of what's going on. So we're going to create these realizations. They're going to be random or directed, but they will be fair. There's no branching. We're going to have, and I'll show that in a minute on another slide, but we'll have one realization of one grade. It'll be paired with another of another grade and so forth. So that this will become clear. So we have this database of realizations. That database is the geological model. Anyone who thinks they can have just one single block model representation of a deposit, and that is the model, that's kind of silly, frankly, right? Because there's geologic variability at all scales. There's just no way in between widely spaced drill holes that you know for sure what's happening. And if you come up with just one number, it's going to be near the middle of the distribution for sure, but it's not going to represent the true state of nature, which has the uncertainty. That's why we use a database of realizations. And then you process all the realizations through the calculations, resource calculations, mine planning, anything you want to do, you look at all the realizations. And this is that picture I was kind of alluding to. And I really want to focus on this one is down on the bottom here. Up at the beginning, and you can kind of read through that faster than I can, frankly. But this is a cartoon representation of how we do numerical geological modeling now. This is the modern approach. So there's parameters that go in to construct the geological model. There's distributions, there's proportions of rock types, there's variograms, there's other parameters that are needed to build the model. Those parameters themselves are uncertain. So that's why down this kind of, if you think about each row being a realization, the modern approach is we have realizations of what the parameters could be because we don't even know for sure what these parameters are. So we might have a model of uncertainty in them, however. So we have these realizations of parameters. We then also have realizations of data. We have missing data. We have data with error, and we don't want to propagate that error through the model. So we'll create realizations, and this sounds really weird, but we're going to create realizations of what the true values might be given what we've observed with measurements with error. So these are actually realizations of true values conditioned to the data with errors, which is kind of a weird way to look at it, but they also have filled all the missing values. We then, for every set of parameters, for every set of data, we build actual geological models. So we build limits, and I'll go through some of the tools very quickly here in a moment. We build geological boundaries, we model rock types, we model multiple variables. And for every set of parameters and data, we build a model. So we have these multiple realizations that I've been talking about. These will allow us, we can look at posterior parameters just to summarize the models. We need to do that to understand sensitivity. Over on the far bottom right here, you're looking at a tornado chart where we're trying to understand what are the major sources of uncertainty? Because it's easy enough to assess uncertainty. That's what we're trying to do here. But when we assess uncertainty, we want to know, where does it come from? What's it due to? How do we explain it? And then if we know where the uncertainty is coming from, we know what to target if our goal is to reduce uncertainty. Sometimes the goal is not to, it's just to understand it. But sometimes we want to reduce it to mitigate risk for decision makers. And then we know the source of that uncertainty and we can target it specifically. So then every realization, we calculate whatever response variables you're after. If you want tonnage of ore within measured, if you want grade of ore measured, you want indicated, inferred, whatever resource numbers, whatever reserve numbers, you can calculate those on every realization. And then you can assemble a distribution. So this red curve here is a distribution. You get the expected value. That's the number you report. There's one number if you want it. You also know the uncertainty. Often we'll summarize that uncertainty by going plus and minus 15% of expected and say, what's the probability to be within there? If that probability is high enough, we're feeling pretty confident. If it's low, well, you know, that's kind of the way it is. And we might want to either reduce it or design a system that's more robust with respect to that. So that's kind of a cartoon view. I'll just give a couple more, just two more history slides, and then I'll dig into some of the techniques and tools. I always like thinking about this, and this is a picture of Edward Teller. Not many people know him anymore. He was, for many years, probably the most famous, however, living physicist. He was the father of the hydrogen bomb. He was on the Manhattan Project. He developed all kinds of stuff. And I remember once going to a talk he gave and at Stanford when I was a student, and there were 5 Nobel laureates sitting in the front row, and the auditorium was packed. And he was giving a talk, not just like a lonely Canadian in their office looking at black squares, right? This was a real talk, okay? So, and he presented his talk. I didn't understand what he was talking about, particle physics and whatnot. But at the end of his talk, there was time for questions, and there was this awkward silence. And one of the graduate students, it must have been a graduate student, very young lady, stood up and said, "Excuse me, Dr. Teller, you've been at the forefront of science for more than 50 years. What has changed the most?" And you know what? You could almost tell the audience was kind of, everyone just leaned forward a little bit because that was kind of why they were there, right? Not really to understand particle physics. And without hesitation, Edward Teller said, back then, so in other words, he was pointing back to the beginning of his career, he said, we thought we could figure everything out. And now we know we can't. And he went on to elaborate. He wasn't talking about the inaccessibility of knowledge. He had made that very clear. He was talking about the fact that we can never sample enough to know for sure what's there. And that, you know, and he was speaking to geostatistics as far as I was concerned, because we'll never drill a deposit enough. We'll never drill it enough to know exactly what's there. The best we can do is understand what we think is there, how uncertain it could be, and then design our resource extraction, our resource management, and everything to be robust with respect to that. So that's ubiquitous in all areas. I probably shouldn't talk about airplanes now and everything else, and in particular, you know, some of the 737s and so forth. But, you know, there was a time where, you know, a lot of design was built on prototyping physical devices. But my point is that really numerical modeling is what's used. It's used a lot, and uncertainty is modeled a lot. Actually, I saw an article in the BBC, I think it was about 2 months ago, where they were talking, where they were revamping a lot of the civil service in the UK. And they were talking about, they wanted people that were familiar with the Monte Carlo method, which is simulation, and, you know, Bayesian statistics. So, and that's what we do. I mean, and it's not just in geological modeling, it's in virtually all modeling. It's accepting and acknowledging there's uncertainty. And it's like, let's quantify it, let's understand it, and let's manage it. Geostatistics, of course, Donnie Krieg and Herb Sichel really got this started. They were trying to understand how to build better resource models. George Matheron, he was a mining engineer, but really a mathematician. His PhD supervisor was Paul Levy, famous mathematician. And George Matheron really formulated a lot of the tools that we use and still use. They've evolved and adapted. He sort of wrote that all down, and he was really the father of this. Let's talk about some of the principles and tools that we use. Just a few principles. First of all, I want to say that geostatistics, it is statistical modeling. It's not geological modeling. I know I'm playing with words a little bit here, but what I mean is we're not using first principles. We're using techniques that are statistical in nature that mimic the character of what we believe is in the subsurface, driven by data and conceptual geological knowledge. You know, some type of modeling is actually based on physics. I occasionally in the past, I've done flow modeling. So if I'm modeling fluid flow through, say, a porous media, I have equations that govern that. There's conservation of mass and energy. There's Darcy's law. There's sort of governing equations that we then discretize and solve. And that's based on physics. And some geologies model that way too, but not in geostatistics. The complex succession of depositional and then diagenetic alteration processes, we might know a lot of them, but the initial and boundary conditions are essentially unknown. Those processes are highly nonlinear and chaotic. There's just no way we could, from first principles, maybe when we get our quantum computing really going, maybe we can, but we can't model from first principles what we have, not to match our drill holes. So we use statistical models, and geostatistics is useful to put geology in numbers. It's useful to estimate, to get a single best estimate. It is useful to quantify the uncertainty, the state of nature that I've talked about. It's useful to plan sample design. How many more drill holes do we need to achieve a target level of uncertainty or to proceed with a different decision? It's useful to transfer that uncertainty through engineering, through economics, through entire project valuation. It does not work well as a black box. And I love black boxes, okay? You know, I love them. And it's just that, I guess I only really like them when they always work. And the tools of geostatistics might not always work because they have to be flexible enough to adapt to different geology. I mean, are you in an iron deposit, a coal deposit? Are you in, you know, modeling some lithium deposit, or what are you doing? I mean, and the tools can be applied to just a huge variety of deposit types, and they're flexible for that, but that means they could be misapplied very easily as well. It also doesn't replace the common need for, or the need for common sense and good judgment. It doesn't save time. It doesn't make modeling easier. I guess that's kind of a down note. Let's get to a happier place. I will say though, you know, why geostatistics? It is the best approach to model the spatial distribution of geological properties at the present time. And I can say that with confidence. And I've got a little screen capture over here about these Kaggle competitions. I don't know how many of you are familiar with those competitions, but they're actually a fairly big deal in machine learning. So what happens is essentially a trusted third party has data. They keep some data out. Some data is provided. Competitors, and there can be thousands of competitors on any one of their competitions, then make predictions, and then they're assessed by the trusted third party with data that's been left out. And let's see who does the best job. And you better believe I do that all the time. I'm checking kriging, I'm checking inverse distance, I'm checking nearest neighbor, I'm checking all the different new techniques that people want to throw out there, you know, just to be sure we're using the right ones, we're using the best. And, you know, I think we should, and, you know, there's people that have been talking about that, even making that a little bit more formalized, because, you know, if we're claiming to build the best models, let's prove it, let's check it. And that's why I like checking those Kaggle competitions to see what techniques are building the best models, being the most predictive. Geostatistics gives us an understanding of heterogeneity and variability. It gives us a framework to integrate multiple data types, soft, imprecise data, maybe geophysical, geochemical, hard data, direct drill core measurements, and so forth. And we can assess that uncertainty and then transfer it through. It is practical and consistent. We have everything set up. And if you actually see how these modern models are built, and I don't have time to explain it all clearly, but if you see how they're all built with essentially a script. Human has a lot of input, but then ultimately the machine does everything according to the script it's given. And that is completely repeatable by anybody in the future. These modern techniques, we're using proven techniques. I emphasize the testing, and they adapt them to the site-specific conditions. They are a hybrid of general methodology, and sometimes we have to customize to particular deposit types. We get a good estimated model, and we simulate for uncertainty, and we target a measure of optimality that's fit for purpose. The way we might build a grade control model for short-term planning is different than we might build a long-term model for resource assessment. And we're always going to be validating and checking these to the greatest extent possible. And automation is coming, and we are going to automate as much as possible. And I see, unfortunately, that what's going to happen to a lot of people, I don't know if it's going to be general geologists, but people that are doing numerical geological modeling, for sure there's going to be some stratification there. There's going to be the experts that really know, and they've studied this and know how to do it and know how to set this up. And then there will be people that are less well-trained that'll be just kind of running things and updating things and so forth. So I can see this dichotomy. I'm not sure it's a good one, but I can see it happening for sure. So we're going to be using intensely and appropriately automated tools. We talked about checking and so forth. What I'd like to do, yeah, and I skipped some of that. Some people get worried if I skip a slide, and don't worry, I gave it, I can take it away. So no problem. But I did want to talk. This is a state-of-the-art kind of seminar. So I wanted to talk about, okay, these are all general principles, and I've spent a long time on those. What are some of the actual tools? What are some of the actual operations? And that's what I wanted to talk through in a series of slides now, so you can see exactly what kind of state-of-the-art algorithms we're using to build the kind of models that I've been alluding to. So there, we have to do a lot of statistics. We do a lot of statistical calculation. We have to do what's called declustering. And it's a lot of the names I'm not sure I agree with, but the principle I do. Whenever you do statistics, you're at the mercy of the sample you have. A lot of times when you drill, you're not targeting to drill in the worst possible areas of the deposit. You might preferentially sample certain areas, certain structures. So getting this, you don't ever take the statistics at face value or the summary of what we see. We have to make them representative of the entire volume we're modeling before we proceed with modeling. So doing good statistics, getting good representative statistics is critically important. We use variograms, and I guess a variogram is kind of the tool of a geostatistician, right? If there's a geostats conference, and there are, somewhere in the logo, they're going to have a variogram. That's just kind of part of the fabric of geostatistics. And the concept is we're trying to understand multivariate dependencies. So the two things, one is kind of what I'm showing here on the left that I'm circling, is the relationship between different variables. Are they directly related? Are they inversely related? How strongly related are they? So we're trying to understand how are the variables related together. And then moving over to the right, this is really what we're thinking about with the variogram, is we're trying to understand, as you have two locations that are further and further apart, how does the variability increase? Or conversely, how continuous is it? Because some deposits, you could be in a plains coal deposit that's continuous over kilometers. You could be in a diamond deposit where it was deposited in such chaotic conditions, it has very little spatial continuity at all. So for every particular geological site and for every variable, we need to understand how spatially variable and continuous it is, each variable, and how related are the variables together. So this is one of the tools. It is state of the art, but it's been around for a long time too. Variograms are part of geostatistics. The other thing that we think about immediately after the variogram as a tool or part of what we do in geostatistics is the whole topic of change of support. The fact is we sample typically with drilling. So you drill some relatively small diameter core of rock, you assay it, and then you composite it to some reasonable length, but that's not the scale of relevance for mining. Mining occurs with fairly large volumes. You've seen the mining equipment. You've seen these shovels approach the mining face. They could be moving literally 100 tons at a go. That's after it's been blasted. So the effective scale of selectivity is significantly larger than the data we have. So one of the things we do in geostatistics is we apply theory and practical tools to understand how things change when we go from our drill core up to a practical support, a scale that's relevant for mining. Because if you start thinking, and that's what this little cartoon down on the lower left's about, if you start thinking about applying a cutoff grade, and if you think about what's happening with the data, which has more variability, but when you think about a larger support, the variability is going to go away. There's going to be some mixing. It's not going to disappear entirely, but you're not going to have the ability to pick out the highs and lows that you might think based on drilling. When you start mining, you might observe that, but you want to make this prediction before you mine because that has a big impact on resources and reserves. So we spend in geostatistics quite a bit of time on that. course, then there's kriging. Kind of interesting, kriging, named in honor of Donnie Krieg, but actually developed by George Matheron. And the concept there is to come up with the best local estimate. This is a little example over here on the bottom right, where the little circles that are colored are data from drilling, and the cool colors are low values, the hotter colors are high values, and then in between the circles are kriged estimates. So this is kind of it's an interpolation algorithm. This kriging uses the variogram, it uses our understanding of support. We can't use a direct data-driven approach that you might do in machine learning because of the configuration. The configurations are somewhat limited. I'll stop, waving this around like a lightsaber. But if I think about, okay, I'll leave it right there. So if the pointer is right there, and if I think about the configuration, now I'm going to wave it around again. If I think about the configuration of data nearby, I may never have replicates of that configuration. So that's where what kriging does is it uses some generalizations about the spatial continuity and the anisotropy and the scale dependent structure and comes up with the best estimate to minimize mean squared error, maximize R squared coefficient of determination. You can play games. We do that. We leave out data. We leave out a drill hole. We predict what we think is there, and then we can compare what we predicted with what was truly there. And we can do that to try to tune our estimates and try to get the best possible estimates. And kriging is the most widely used. If you look at all the JORC reports, all the NI 43101 reports, say what technique did they use to estimate their resources? Number one, ordinary kriging. Number two, inverse distance, but it's second by quite a margin. Ordinary kriging is the number one technique for resource estimation. What's being done increasingly is that people want to use and harness some of the techniques that are available in machine learning. And you know what? I'm 100% supportive of that. In fact, this was a one-slide summary of some work that I've done recently with a student, which we've published. And if you want anything, you just contact me, I'll let you know. But the whole idea now, and this is coming out of a lot of those Kaggle competitions and all this other stuff, is that people use ensembles. So for this is really hard to understand, I know, but just think about having some data in space, and it's not just 2 dimensions, of course it's 3D. And you could go down the machine learning route, and there's a whole bunch of different techniques, all that have pros and cons, but you try them all, and then basically you're using essentially a super learner that's on top of these different techniques. So what you're trying to do is combine these together to get the best possible one. Then we go down the variogram route, and we go into kriging. Now, kriging has some really strong advantages, especially near data, because it reproduces data exactly as it should. So then we combine the machine learning with the kriging to get the final predicted map. And we're going to optimize to do that because we want to get the very best estimates. Actually, I was at a conference in Brisbane a number of years ago, and I remember there was, they invited some guy from IT, some high tech, whatever, to come in and give a keynote talk. And I remember in his talk, I was sipping a cup of coffee in the conference hall during the keynote talk that he was giving. And he mentioned that, if you can't get things that are like 50% or 100% better, then you're not doing innovation. And I was like, and I almost choked because you know what? We're aiming for a few percent better. Okay. If we can get our resource models and we can improve them by a few percent and keep making them a little bit better and better, and you just send a few more truckloads, for example, of ore to the correct place, they go to the plant rather than going to the dump, and you send a few more truckloads of waste to the dump rather than going to the mill. If you can just make things a little bit better, you're having a big, big impact in getting those resources right. So of course he was in a different discipline. I'm not being critical, but I'm just saying we strive for whatever improvements we can get. This picture, I've used this picture a lot. I very much like it. This was the frontispiece on the first book I ever wrote. And the idea that I was trying to convey is there is a truth. It is out there. It is variable. We can drill it. We can sample it. If you do kriging, our representation is very smooth. It doesn't look like the truth. It's going to be much smoother, particularly in areas that are wider spaced. Of course, it's going to be smoother. The concept of simulation, however, is to create these alternative realizations where the variability is like the truth. They match the data. they match the variogram, they match the statistical controls, they are non-unique. And I know that causes a number of you heartburn. The fact you don't get one model and you get a set of models. Once you accept that you can just deal with them all, no more heartburn, okay? Because then you just use them. And if you want to know, okay, what are our measured resources? Calculate the measured resources in every realization, take the expected value at the end, and that's your measured resources. You can use them all. You don't have to pick one. You don't need one. You need to understand how different it could be, especially when the data spacing becomes wider. And then if the data spacing is very similar, then all the realizations are very similar and there's no uncertainty, and maybe you just take one number. But the modern approach is to simulate. It is to understand that uncertainty. And you start out, when you do that, by modeling large-scale boundaries. So all of our simulation of mineral deposits, we would never do that kind of in one step, go directly to grade. No. It's all a hierarchical approach. So we would model bounding surfaces, either as triangular, faceted surfaces, or we might model just two-dimensional bounding surfaces. We might modify our grid. Sometimes we can even do this grid-free. There's some emerging techniques where you actually model things free of a grid, not free of coordinates, but free of the grid. So we model boundaries, and sometimes that's called implicit modeling. When we do that, we try to capture a lot of the curvilinear, the different directions, our geological interpretation. We model these volumes within which we're going to then go ahead and assign rock properties. But we start at a large scale, we move to smaller scale. When we move to smaller scale, sometimes we'll use these process mimicking models, which are kind of cool. So we actually numerically model the geological process. It's not truly the process, but we mimic what could have happened. Certain sedimentary environments, lateritic weathering environments, some structural environments of fluids flowing through a fractured rock mass. We can actually model kind of using more of the physics. So we get our numerical models that actually replicate better the geological structures. Here's another example, and this is, I took this in a photo, this is near Drumheller in Alberta here, a number of years ago, but you can see some of these structures that we were then, mimicking by our model, and it's very dynamic. So we'll model within the larger scale envelope. Sometimes we'll model these structures with as much physics as we can. A lot of times we have to use a more numerical approach. This one is kind of cool, this technique. It's called hierarchical. It's just like jargon. I know for some of you coming from a different geological background, it just means nothing, right? But anyway, I apologize for that. This hierarchical truncated plurigaussian. So this little cartoon over on the right, I think makes some sense to understand how this works. So what we do is, let's say you had three different structures, and I know it's a cartoon, it's always more complicated than that. But you say you have three different structures, then at the bottom you got three other layered, and then you have this discordant dike, and you can see this erosion. Well, we devise a truncation scheme where you separate what's on top from what's on the bottom. Then you separate the discordant feature from the others, and then you separate those. So you design a system of how to get the rock types that have the correct interrelationships when we do the model. So that's actually kind of cool. So within the bounding surfaces, within the implicit model, we'll then model categorical variables. So of course we model surfaces, we model categories within surfaces, then we model continuous variables within the categories. So it's all, the machine's doing the work, okay? So we don't have to, necessarily remember everything. It's all scripted, so we can do this modeling in a organized fashion. I did want to throw in this slide on trend modeling, because one thing that comes up a lot in statistics is stationarity. This concept that the statistical properties are the same everywhere within a particular rock type. The fact is they're not. So nowadays, the modern approach in geostatistics is, even within a deemed homogeneous rock type that might be considered stationary, we have a large scale trend, and we try to model that trend, and then we remove the trend. So you can see this, only an engineer would do this, right? Put a correlation with 3 significant digits. But we remove the dependency on the trend. We can model that detrended variable, and then we put it back. So we try to capture that non-stationarity. Another technique I want to mention, I think this one's a really cool. It's been used a lot. This is an example. This is actually from, I believe, a nickel laterite. And you can see, well, these are just little postage stamp things. You can't see too much. But these are bivariate scatter plots between different variables. And you can see the complex structures on those. And I remember I was giving a talk a while back, and I pointed to this one, and it seemed to me like it was like one of those Vulcan spaceships that was diving. And there was some guy in the audience who was from Texas. I love people in Texas. I lived there, worked there, whatever. With this fellow in the audience from Texas, and he said, "No, it looks like a duck with its head shot off." I was like, "Geez, it's a little dark." But anyway, these relationships are complex. You can see constraints. You can see all kinds of different features. That's not going to work well in our geostatistical tools. So what we have to do is we transform the data with very complex features over to a transform variable space that are uncorrelated and completely independent. We can then do our numerical modeling much easier. And then when we're finished, we back transform and these come back again. So it's not like we're getting rid of it. We're just embedding the complexity in the transform so that the modeling is facilitated. And in the transform and back transform, we remove and then reintroduce that. So that's really common. I had this little video here. I don't know if I can show it. It's not a, it's the idea of taking a distribution, and what it's doing is it's finding where things are weird. I know that's not very technical. It's finding where there's most complexity, and then it's transforming it. So it's kind of going through the data. And of course, this occurs in a high dimension. So it's just projecting the data, finding out where it doesn't look good, making it better. And now it's finished, by the way. It's at iteration 10. And when you're finished, you can see that the data are completely independent. If I took a slice here, the range of variability is the same as if I took a slice here or here. So I remove all that complexity. That's this projection pursuit idea. And then we do our modeling and we reintroduce it. It is honestly state of the art. That's what we do. The other thing that's important for uncertainty and for understanding resource uncertainty is parameter uncertainty. I mentioned that already. Remember I mentioned those prior parameters. The parameters themselves are uncertainty, the input histograms, input variograms, and so forth. So I just wanted to bring out in a talk like this, I know we're not a detailed technical talk, but I wanted to mention that the correct approach to parameter uncertainty is known. We know how to do it. And it is a little weird because, uncertainty in the parameters, and then there's uncertainty in how we get the uncertainty in the parameters. And you should be worried about the potential for some sort of circular quest. But based on a lot of studies where this is an image that was actually taken from NASA, where we've taken these very large images of natural processes, you can tell it's not really well, it's the Earth, so I guess it's geological by definition. But we take these exhaustive images, and then we essentially take a configuration of drilling, and we find similar circumstances where you get the same drill holes. And then we see, well, how different could the parameters really be for the exact same drill holes? So if you think they're the same, how different are they? And then we develop mathematical techniques that will give us the correct uncertainty, and that's the green triangles in this case, or here, this is just showing the correct approach based on the direct observation of how uncertain really are the parameters. So we do a lot of this kind of analysis to find out the techniques that actually work. We build a lot of block models. That's kind of what's shown in the upper right. Shown a little bit down on the bottom is more on a grade control, but we build block models for different purposes. Like I said, they're almost always hierarchical. We'll build them in estimation mode where you get a single best estimate. We'll build them in simulation mode where we get multiple realizations. And then we'll do grade control. Grade control is slightly different. You model at a very high resolution. You model kind of the expected profit of what's happening at a very high resolution. You model the blast movement. Then you get big limits that are practical and mineable and send the material to the correct destination. It's a big part of what geostatistics is all about. I mentioned about checking and validation. I'm not going to talk through this. I just want to reinforce to you that checking, that validation, that assessment with data that have been left out, that assessment with real data. That's something geostatisticians take very seriously. We know we're playing with fire in a way. We're building models that are based on 1/1,000,000th of the mass being sampled, and then we're inferring everything with our numerical model. We know there's many, many decisions that have to be checked carefully before the models can actually be used. Talk's almost over. Don't worry. You might think I'm on a runaway railroad train, whatever. It's going to go on forever. I probably could, but we're almost done. I did want to have a couple slides on managing uncertainty, though. And I wanted to stress the fact that there's some bad ideas. Choosing one model or averaging all the realizations and using the average is kind of a bad idea. It's not bad to use the realizations through a fixed design, but really we should just use all the realizations. You use them all. This is a resource number. You get the expected resource, whatever the units are. You get a distribution of uncertainty. You can get, okay, what's the probability to be within 15%? So you just, how many realizations are 1.15 times expected? Between that and 0.85. So we just use all the realizations. You can report with the multiple realizations. So you can report the expected. You could report directly the uncertainty too. So that can be done. Most often though, uncertainty in mining is captured in the classification criteria, measured, indicated, inferred, or proven probable. So that's how we normally, so we get the uncertainty, we make sure it fits properly in one of those bins, and those bins are how the uncertainty is communicated to the public. The estimates come from all the realizations. So we use them all, we take the expected value, we then also understand what is the sensitivity. Where is the uncertainty coming from? Is it coming from geological boundaries? Is it coming from rock types? Is it coming from grades? Is it coming from the parameters? Is it coming from the histogram, the variogram? Where is the uncertainty coming from? And then we can use that whole efficient frontier. Here's an example with pit design. So if you optimize the pit on each realization, none of them are very good. Well, they're okay, but that's these blue dots. But you can optimize the best possible return, and it could be associated with a certain amount of risk. You can penalize risk and optimize, so you're going to get a little bit lower value, but you're going to get lower risk. So these red points are on this efficient frontier because there is a trade-off. If you want to mitigate risk, you can change your decision to get less risk, but you're going to pay for it in expected value. But we can do that quantitatively, and that helps us with our decision. Trying to stick to my 45-minute time. I'm past, well, you know what? I'm close to 45 minutes total, honestly. I just got two slides. One I wanted to mention is resources. I've gone through this, and honestly, you guys are like drinking from a fire hose. There's no way you can take it all in, but you can kind of get, maybe you're intrigued by something. So there's lots of sources. There's lots of books. I've published 8 books and a whole bunch of papers, including mine. I put in the smiley face to, dampen my shameless self-promotion, which, everybody who knows me knows that's part of my fabric, so no big deal. I will mention a couple websites. Geostatistics.lessons.com. I keep with my students adding a lot of lessons to that. I think we're up to almost 30. So a lot of the topics that were mentioned here today, there's a lesson. So there's like a 5 to 10 page lesson on it. Strongly recommend you have a look at it. You can look at CCG Alberta. That's my research group. From a corporate perspective, resource modeling solutions, highly recommend that. We got our 2022 training offerings. I don't know how many classes we're going to have. I think 12 to 14 classes. And those classes they've been, quite well attended over the years, and you could have a look at that as well. One last slide, and then I'll happy to look over at questions. I just glanced at the chat and I'm seeing a lot of verbiage there. I don't know. I'll do the best I can. But let's wrap up. History of geostatistics is classical. And you know what? You could say that about almost any discipline. You do things by hand until you get the machine, the computer. Then you use the computer to do what you did by hand. Then you become creative and you start using the computer to do things you could never do by hand. That whole quantification of uncertainty, you never could do it by hand. You could never, automate to the extent that you need to. I will comment, I know there's the truth. The truth is out there. There's a unique single truth for every mineral deposit. The thing is, it's unknown. and we have sparse sampling, and there's geologic variability at all scales. And that's why we go down the path that I've explained to you. We do estimation and simulation. They're suitable to build those quantitative numerical models. We can use them to understand risk, and we can optimize our decisions. And yeah, I think that's a fair summary. And I'm looking at the time. It's kind of weird. Usually I'm giving a talk because I'm still old enough to not be entirely dominated by the last 2 years. I'm used to having people out there. So now I finished the talk and I'm just looking around my office, and but that's it. The talk's over. Let me look at the chat and see if there's any questions to answer. And we'll let the moderator jump in too. So, yes.
Okay, thank you very much, Clayton. That for sure is very interesting. I can read some of the questions for you if you don't mind. So maybe the first one, not in any particular order, is pre-concentration ore sorting offers great uplift before milling by removing waste. How can geostats assist in understanding what level of variability may be exploited by sorting at a sub-SMU scale post-mining?
Yeah, no, that's a good question. There's no doubt. And there's no doubt that some of that ore sorting, like a lot of things, it's probably, tremendously helpful in some circumstances, and maybe doesn't actually provide much in others, right? It really depends on a lot of things, I'm sure. But there's no doubt in my mind that it has great potential in many circumstances. What geostatistics provides is the ability to model the variability at any scale. So I remember recently, actually, for the same kind of thing, the ore sorting problem for a uranium deposit, recently we built a model where we were actually modeling at essentially a cubic decimeter scale, because we thought that's kind of some of the scale that might be considered. So you can model geostatistically at that, and then you can numerically model the efficacy or variety of potential efficacies of some of that ore sorting. And you can essentially feed those numerical models by the high resolution geostatistical models. And you can do that to get some of the sensitivity, to get some of the understanding, and to value just what it's worth and what measurements are needed and so forth. So I think there's, for numerical modeling of that ore sorting, the geostatistics provides that front end input that could be useful.
Okay, thanks. The next one, it looks like a short one. So is, why don't we routinely report for plus minus uncertainties on resource grade and tonnage estimates?
Yep, no, that's a very good question. The other one was too. The reason is the conventional practice in mining is the uncertainty is reported by a classification. So measured, indicated, inferred, proven, and probable. So technically, we do quantify the plus minus uncertainty, and that allows us to decide what bin it falls in. And for public disclosure, it's those classification bins, measured, indicated, inferred. The reason we don't do both is it's not universal. So if somebody did it and somebody else didn't do it, then the people that did do it might be penalized by showing the uncertainty. So what we do is we consistently and uniformly classify into those bins that have a regulatory and public understanding of confidence.
Right, the next one says, interesting talk, thanks Clayton. In geochemistry, there's been a growing trend of treating compositions after some transformations to account for their proportional nature. In your experience, does such data treatment improve modeling outcomes or not particularly?
Yes, it does. And in fact, there's only so much I can explain in the 1 hour overview talk like this. But even before we go into that PPMT transform where I said we make it easy, if we have compositional data, we'll go through one of those transforms. Usually I'll just use a simple one, but using you don't need to use a logarithm, but using some ratio type transformation, then you go through the subsequent transformations, and then that goes into the back chain of transforms, will enforce the compositional constraint. And that's, it does improve things for sure. And throwing those compositional constraints in with the other ones is how we achieve that. Yeah.
Okay, another one. How do we think market would respond to reporting, including uncertainty? And if using the classification approach, inferred, indicate, and so on, is guidance regulation required? as one person's indicated is another's infers based on an acceptable uncertainty?
Yeah, that's interesting question. And there is necessarily some ambiguity in what exactly is measured or indicated. But that is the best we have in the mining industry right now. And you know what, in some circumstances, given the different data types, given different nature of uncertainty, the absolute uncertainty that might be acceptable could be different from one deposit to another. And that's the role of the competent or qualified person. So now I believe it's not a perfect system. It's flawed. All systems are flawed. But I do believe that the systems that are embedded within JORC or 43101, which place reliance on the competent person to make some judgments, I think that's the fair and correct thing to do. If somebody wants to call something measured that's highly uncertain, sooner or later, they're going to get caught out, found out, and that's going to be the challenging for them. So there are some standards. So I do believe that using those classifications is the right thing to do.
Yeah, I think the next one, it's more like, it sounds more like a comment referred to the previous one. So maybe you'd like to comment on this. So it says, but what is not uniform is the definition of measured, indicated, or inferred.
Yeah, it's not uniform, but it's actually fairly clear. There's understandings that, you know, people understand that measured, you have there's supposed to be a high degree of confidence in the geological continuity in the presence of the resource you're reporting. Now, it's not stated that it has to be, like if I had to say a number, I would say something can only be measured, and this is my assessment, if a monthly production volume would be within 15% of predicted with a 90% probability or higher. But then some people say, well, we don't need a month, a quarter's fine by our standards. And I'm like, okay, well, that's the role of the competent or qualified person. So I agree that it's not a uniform definition, but it is fairly precise. If you go into JORC, you go to 43101 and go into the different CIM guidelines and everything going with that, it's not, you can't just do anything you want. If you do, like I said, you report measured that's supposed to have a high degree of confidence and it's found out to be very different, there's going to be consequences.
All right, the next one. Thank you. Can you comment on the spotted dog effect regarding classification? I like to have some control over the classification rather than relying on calculated parameters. Does that make sense?
Whenever somebody asks, does it make sense? I usually just want to say no and stop there. No, yes, it does make sense. And you know what? I would never, and I have a paper out there in SME mining engineering saying I would never base classification directly on the results of simulation. It should be indirect. The results of simulation support what is the uncertainty for particular data spacing. You use those geometric data spacing criteria in the classification. You don't directly use the uncertainty. The uncertainty is related to something more physical because you want that more kind of transparent and open criteria for classification. So yes, it does make sense. And simulation supports the geometric criteria that you should use for classification.
Okay, another one. Is there value in measuring uncertainty at every level of modeling, life of mine, short-term models down to grade blocks?
Yeah, you know what? At a short term, no, modeling the uncertainty doesn't help. Modeling the variability to optimize the decision. So you make sure in a short-term model, the number one criteria is the destination, sending it to the right place. So there, the uncertainty is kind of irrelevant. You just want to get it to the right place. So yeah, no, you don't need it there. At a long term, a really long term, maybe the uncertainty is so big, it's so big, you just want to understand how to go forward with exploration. Maybe you don't trust your quantified uncertainty. But once you get into the pre-feasibility, feasibility, yeah, understanding the uncertainty is important. But to answer the question, no, there's no value in measuring the uncertainty at every single stage.
Another one, assessing the estimator's competency is becoming more likely in public reporting of resources and reserves. How would you do it?
How would I do it? Yeah, well, I'd make them take a class that I taught and then I would judge how well they did, and I would have oral exams. No, I'm just kidding. I don't know, that's tough. You know, there's clearly some requirement to have experience, right? You can't, it doesn't matter how well trained you are. If you don't have experience, you're not qualified, frankly. You need experience. You do need to have the appropriate training. You do need to have the appropriate QA, QC in terms of the process of modeling, and you have to respect that. You have to have the appropriate reviews and so forth. So I think as much as nobody likes to be judged, you're absolutely right. We are going to be judged. We should be judged, even though we don't like it. And we should set ourselves up with a process of modeling that has every chance of success and has every chance of catching a preventable error from slipping through. So yes, I would follow kind of those principles.
Okay, a few more questions. So could you provide more information on the differences between using machine learning to generate missing data versus using data imputation?
Yeah, you know, that's an interesting question. I have to say that the whole line now is blurring. In fact, everybody's using machine learning. So it's like, it's really hard to draw a line and say, oh, we use machine learning or we use something else, because just as I showed in that one slide, we often mix machine learning with kriging, and we mix it with other techniques. So it's not exactly a kind of a clear demarcation anymore. But you know, the one thing I will say about the more classical geostatistical imputation is that it more honestly accounts for uncertainty. If you use machine learning, you get a single estimate. So it might be a best estimate, but it doesn't necessarily account for uncertainty. So which one I would choose would depend on how important I felt it was to capture that uncertainty. If I just wanted a best model, I'd probably go machine learning. If I wanted uncertainty, I'd probably go with the classical techniques.
All right, so next one. From your experience, what combination of parameters do you use to optimize resource classification? Sample SR, kriging efficiency, number of samples, and so on.
Yeah, you know what? I don't use slope of regression. I don't use kriging efficiency. You know, you can change those by changing block sizes and fiddling with searches. So I don't find those dependable and reliable. And I know some people might be upset, but you know what? That's fine. I would primarily use measures that are geometric in nature, drill hole spacing, calculated by one means or another, or even say data within a search. I do believe classification should be based on the amount of data you have to support the estimate within some different geological domains, because some domains are inherently more uncertain than others and might need more data. So I want the simplest geometric criteria. I don't want slope of regression. I don't want kriging efficiency. The number of samples, perhaps.
Okay, so something related to samples now. So to talk about modeling. So what data would you like to see collected? Are there any new developments in data collection that can make a significant difference in model estimates?
Yeah, actually, it is interesting. Geostatistics is data-driven. Everything we do is based on the data we have available to us. So it's critically important to have data. Now, there's a trade-off between sort of very precise measurements and maybe more indirect measurements. So sometimes I think that's what I want to see is the most data, all the data, as much data as I can get. Okay, but realistically, some sort of a trade-off or some sort of between getting hard, precise measurements that may be expensive and widely spaced, and maybe some even less expensive drilling or less expensive sampling, but you can get more extensive coverage with that. So getting a combination of the two and even thinking about trying to optimize that, I think that would be relevant. We want to measure things that are directly related to the economic performance of what we're assessing. So obviously we need grade variables. We may need to model important or measure important contaminants. Some other measurements that might give us an insight into metallurgical properties, throughput, recovery, energy consumption, reagent consumption, those kind of variables. Anything that gives us insight into that, we would want to collect.
Okay, so I think probably last question, so we don't keep you too much with this. So do you have any tips on how to deal with the nugget effect?
Yes. First comment I'll make is the nugget effect is neither good nor bad. It just is. Okay. What I would recommend though is that we should infer the best possible, most representative nugget effect. Don't just take a nugget effect off some, automatic variogram fit. That would be a travesty. Take some care and attention to get the best possible nugget effect, use the best possible directional variograms, maybe even do compositing to different scales and look how the variance changes and infer the nugget effect that way. So get the best possible nugget effect that truly represents the short scale variability, and then you got to live with it. So it's not, a nugget effect's neither good nor bad, it just is, but you want the right one. And so my only tip is to take care and try to get the right nugget effect.
Well, Clayton, thank you very much. I think you've been generous, very generous with both giving this presentation, also answering lots of questions. And I'm sure we'll hear again from you. So thank you very much again for your time and for agreeing to present for us today.